Coming down to the next concept, that is about self-induction and mutual induction. A pretty interesting concept as far as electromagnetic induction is concerned. Let's consider a soft iron core material. Why we are selecting a soft iron core material? Purely because of its magnetic properties. I'm having a rectangular frame which is hollow from inside, but at the same time is a solid rectangular iron frame. This solid rectangular iron frame has a certain number of coils that are wound across the first arm. When we see that current is made to pass through it, this current sets up its own magnetic field. We know that when current is made to flow through a coil, definitely it sets up its own magnetic field. So this coil produces its own magnetic field. Now this coil is basically wound across what? Is wound across a rectangular iron core material. And when it is wound across a rectangular iron core material, we see that it is inducing its magnetic property into the core material. So this type of induction wherein this external coil which is carrying a current is inducing its magnetic property onto the iron core material is called as self-induction. A similar experiment you studied in 9th. We had a bar magnet and we cling a pin, an iron pin towards it. What do we see? We see that this bar magnet transfers its magnetic properties to the iron pin. Furthermore, this iron pin gets converted into a magnet. Now, when this iron pin has converted into a magnet and we take another pin towards it, we see that it attracts the second pin. We see that it attracts the second pin. Why does it attract the second pin? Because it itself has got converted into a magnet. Because it itself has got converted into a magnet. This continues so long as the magnetic properties are getting transferred. But however, if I remove the initial bar magnet, the pin no longer retains its magnetic property. So we see that all the remaining pins get demagnetized, as a result fall off. This happens because of the phenomena of self-induction. Similar is the case over here. Only thing here is that the source that is producing the magnetic field is the electric current. So we have the electric current that is made to pass through a circular coil, which is setting up its own magnetic field. This magnetic field is allowed to permeate through the magnetic iron core material, thereby converting it into magnet. That means it has induced its magnetic property onto the iron core material. Such type of phenomena is called as self-induction. A very simple phenomena. Going on a higher version, wherein we go in for mutual induction. The setup is almost the same. We have the rectangular iron core material. We have the first coil that is wound across it. The same current is passed through it. As a result, it is setting up its own magnetic field and is allowing it to permeate through the magnetic core material, thereby magnetizing it. So the first part is the same. However, the advanced version is across the opposite arm. Across the opposite arm, we are wounding another set of coil, which we call as the secondary coil. Now, when I wound such type of coil across the opposite arm, what is happening? We are seeing that magnetic lines of forces are entering the secondary coil. And in the earlier experiment we saw, when the north pole of the magnet enters the coil, it generates an electric current. So definitely when magnetic lines of forces are entering the secondary coil, we see that it is going to generate a secondary current as well as a secondary voltage. So that means it is because of the induction of the first coil, the second is inducing its magnetism. So we see, or we say in this case, that this particular phenomena is called as mutual induction. Because it is the change in magnetic flux of the first coil that is causing a change in magnetic flux across the second coil. The first coil where the input is supplied is called as a primary. The second coil across which we are obtaining the output is called the secondary. the device, the industrial device that works on such a principle is called as a transformer. There are two types of transformers, broadly classified into two types: step-up transformer and step-down transformer. Talking about step-up transformer, definitely the word is indicative. I have to step up the voltage at the secondary end, or I have to step up the current across the secondary end. The moment I'm talking of stepping up, that means I have to correlate it with which law? The first law that we studied. Yes, Faraday's law of electromagnetic induction. Why? Because we say I is directly proportional to the number of turns of the coil. That means greater the number of turns of the coil across the secondary as compared to primary, more is going to be the output voltage. True or false? True. As a result, we see that in a step-up transformer, the number of turns in secondary coil is more than the number of turns in the primary coil. This is one of the difference between a step-up transformer and a step-down transformer. Secondly, as I said, we have to obtain a larger output across the secondary. A larger output meaning thereby larger voltage, larger current. And if I have to have large current, that means the resistance should be low. When the resistance is low, we see that the wire is thicker in cross-sectional area. Why? Because we have the relation. The resistance is inversely proportional to the area of cross-section. Greater the area of cross-section, less is the resistance. So therefore, we definitely have the secondary wires thicker than the primary wires in case of a step-up transformer. This is the second difference for step-up and step-down. Talking about step-down transformer. Again, as I said, I have to reduce the voltage across the secondary. Reduction of voltage across the secondary indirectly relates to the number of turns of the coil. That means the number of turns at the secondary should be lower than the number of turns of the primary. In comparison with primary and secondary, I see that number of turns in secondary less than number of turns in primary. At the same time, I want lower output towards the secondary. If I have to have lower output at the secondary, definitely the output current should be low. The output current will be low when the resistance is high. The resistance will be high if the wire is thinner. That means area of cross section is less as compared to primary. So my secondary coil is thinner as compared to the primary in case of a step-down transformer. Practical applications of this, tremendous. I'll just quote one simple day-to-day example. Most of you today have your cell phones, right? We keep the cell phone for charging whenever the battery is run down. Now this charger or the adapter, what we call in commercial terms, what exactly is this adapter? Have you ever thought about it? See, what happens in this case is that your main supply is giving you a voltage of 220 volts. What is fed into the mobile is just 12 volts. So that means there is a drop of voltage from 220 volts to 12 volts. So there is definitely a drop of voltage. So what should be the device that should be used across over here? Yes, it is a step-down transformer. So one of the very good examples for step-down transformer are the adapters that we use for charging your mobiles. Step-up transformer, definitely in heavy-duty industries, we do have to increase the voltage as compared to a commercial one. So whatever commercial voltage we get across on a day-to-day basis to the consumer is 220 volts. In order to apply to heavy-duty industries, we take a voltage of almost 11 kV, 11,000 volts. For that, we have to step up the particular voltage. This is done with the help of step-up transformer. So if you go across any of these MIDCs area, industrial belts, you will see huge transformers that are put across in order to step up the voltage. Coming down to the next part. Talking about the next part, we have something what is known as the losses that are incurred in this. How do we account for the loss? It's a device, so definitely there will be certain amount of losses. The first loss that is incurred over here in case of a transformer is the eddy current loss. What is this eddy current loss? As I said, this particular soft iron laminated core material is the one that has been induced with magnetism. Now this magnetism also produces certain amount of stray electric currents, which are called as eddy currents. Now these stray eddy currents are not taking part in the induction of magnetic flux. So what is the counter effect of these eddy currents? They basically warm up the core material. So again, reverting back to your day-to-day example, if you look at the mobile charger, if you excessively charge your mobile, we see that this particular adapter melts or becomes warm after a certain interval of time. Why does that happen? It is only because of this leakage of eddy currents that is occurring, which causes the heating effect of the transformer. So eddy currents are nothing but the stray currents that produce a heating effect in the transformer. Second type of loss that is incurred is hysteresis loss. Talking about the hysteresis loss, again, reverting back to the basic figure of self-induction. As I said, we have a coil that is wound across a laminated core material. This coil is setting up a magnetic field across the core material. So it is magnetizing it. Once it is magnetizing it, that means each part of the core material starts behaving as a magnet. When it starts behaving as a magnet, that means each part has its own magnetic field. Is it that this magnetic field is taking part in the permeation? No. So these losses that are incurred on account of the core material getting converted into a magnet, on account of its own magnetic field, is definitely a loss as far as this is concerned. And we reduce these losses by laminating it with insulated material like mica. So both these losses can be eliminated in terms of laminating the soft iron core with terms of laminated material such as mica, insulating material such as mica. There is a third type of loss also, which is a very minor loss, but still we do consider it, because we are using a coil which is a wire. Though a good conductor of electricity, will definitely offer certain amount of resistance. So whatever is the input current that we are expected to get, we do not utilize it in the induction process because of the resistance that is offered by the wire. So definitely those losses are also incurred as far as a transformer is concerned. Well, when we studied transformer, we said we have a step-up transformer and step-down transformer. There is something what is known as a transformation ratio. Now this transformation ratio is again very indicative. What is it that it is transforming? What is it that it is converting? Basically, it is converting a voltage that is given at the primary to a voltage that is coming out at the secondary. So the transformation ratio works out in terms of number of turns, works out in terms of current, works out in terms of voltage. So if I have to give the ratio, I say it is number of turns of secondary to the number of turns of primary. Transformation ratio of a transformer is number of turns of the secondary divided by number of turns of primary equal to current in secondary divided by current in primary is also equal to voltage in primary divided by voltage in secondary. Remember, VPIP is equal to VSIS. Wherein if I cross multiply, I say that voltage of primary into current of primary is voltage of secondary multiplied by current in primary. Again, as I said, this is just a ratio that you should know purely to understand what exactly the transformer is doing. It has nothing to do with numericals. You never ever get numericals based on this. It's only a theoretical concept which you should know as to what exactly is it when we say it is a transformation ratio. We should know this as a theoretical concept, just to know it as a concept and not from numerical point of view. Let's consider three major appliances that are using the concept of electromagnetic induction. The first very important one is the concept of electric bell. When I talk about the electric bell, definitely everybody recollects the doorbell that is there across the house at the main entrance. Now, do you ever know that this particular bell works on the principle of electromagnetic induction? Well, for a know-how, it must be a new concept. But yes, it does use the concept of electromagnetic induction. Let's see how this is done. As far as the bell construction is concerned, we have the gong, we have the hammer, we have the armature, we have an electromagnet that is being connected, and then we have the two terminals along with the switch. What happens in this case? When I put on the switch, when I press the switch while pressing the doorbell, I see that the current is made to flow through the electromagnetic coil. The moment current is flowing through the electromagnet, it is creating it, or it is inducing its magnetic field across the electromagnet. Now this magnetic field that is setting across the electromagnet is converting the polarity of the magnet into North Pole and South Pole. So the arms of the electromagnet are getting magnetized. As a result, they are attracting the armature towards it. The moment they are attracting the armature towards it, we see that this armature is carrying the hammer. That hammer goes and strikes the gong, and then in the negative half cycle, since it's an alternating current that is moving across, in the negative half cycle, the electromagnet gets demagnetized. As a result, we see that there is an intermittent supply of current. And because of this intermittent supply of current, we see that this particular bell keeps on ringing. Another way to explain the same phenomena is that this armature is basically connected to a contact adjustment screw. The moment it gets magnetized, the hammer strikes the gong. But then because it has left its contact with the screw, it gets demagnetized, the circuit is broken. And when the circuit is being broken, this armature again returns back to its original position. Again the circuit gets completed. Again the electromagnet gets magnetized. Again attracts the hammer, striking the gong. So in both the ways we can explain how the intermittent ringing of bell occurs. This is purely because of the consistent action of magnetization and demagnetization of the electromagnet, which occurs because the current that is set across are in two phases. One is a positive half cycle, the other is a negative half cycle. The second appliance that we are going to consider is a DC motor. Again, a DC motor has a very good application as far as a day-to-day practice is concerned, is about your ceiling fan or any fan for that purpose. It runs on a motor. Okay. Now this motor is nothing but it is a device that is causing a rotational motion in it. How does this rotational motion come across? This rotational motion is being generated from the electrical energy that is being supplied. That is why when I put on the button for the fan, I see that the electric current is made to flow through it. As a result, the coil starts rotating. Well, this is just a know-how explanation, but then going into the details of it, a DC motor basically consists of a horseshoe magnet with concave poles. It is a coil that is being connected across, and you see the various paths that are shown over here. Well, when electric current is made to flow through the coil, we see when current is made to flow through a coil, it is setting up its own magnetic field. This coil is being introduced in an external magnetic field. When it is coming under the influence of an external magnetic field, definitely it will experience a force of attraction or repulsion, because of which we see that it is going to tend to rotate as it is fixed about a axis. This coil starts rotating. Because of rotational inertia, we see that it completes one rotation. One rotation that is from 0 degrees to 180 degrees. However, because of restoring couple, it will continue to rotate in the same state of rotation, thereby completing the further rotation of 180 degrees to 360 degrees. So this rotation keeps on going so long as the current is flowing through it. And we have a variable rheostat that is connected. in order to increase or decrease the speed of rotation. That is what we call as a speed regulator as far as our fans are concerned. The moment I increase the speed, that means I am reducing the resistance. When I am reducing the resistance, more is the current that is flowing through it, faster is the coil that will rotate. So I definitely have the magnetic lines of forces being cut over here as far as the coil is concerned, and more the number of turns of coils are being cut, definitely I see more the current that is generated, and faster is the speed of rotation of the DC motor. The third appliance that I consider is an AC generator. In case of AC generator, we have the conversion of mechanical kinetic rotational energy into electrical energy. That's something what is known as a dynamo. You must have seen in earlier days, even nowadays, if you have cycle that has been fitted with a torch lamp, the moment you keep on paddling the bicycle faster and faster, that means you are supplying it with larger mechanical kinetic rotational energy. So faster you keep on paddling, the more is the current that is generated and the brighter the torch glows. So long as the mechanical kinetic rotational motion is getting converted into electrical energy, we see that there is a generation of electric current. So again, with the reference to the figure, I see that the coil is basically introduced into the plane of the coil. The plane of the coil is introduced in the magnetic field. When it is introduced in the magnetic field, we are considering the position wherein it is parallel to the magnetic field. So least number of magnetic lines of flux are being cut. At this position, we say that the output EMF is almost nil, that is zero. The moment I supply it with a mechanical force, that means the coil is made to rotate, slowly and steadily we see that the angle which the coil is making with the magnetic field is changing. So it is increasing slowly and steadily till it becomes perpendicular to the field. The moment it becomes perpendicular to the field, we see that maximum lines of magnetic flux are cut. That means maximum EMF is being generated. So when I am plotting a graph, as the coil is moving across, we see that the graph is reaching its peak value at 90 degrees of rotation. Again, as I said, because of the mechanical force that is being given, it is rotating still further till it completes 180 degrees of rotation. This 180 degrees of rotation, again we see that it is parallel to the magnetic lines of force. As a result, the EMF induced is zero. But then it has already completed one positive cycle while traveling from one end to the other. Because of rotational inertia, it will continue to move further till it completes 270 degrees of rotation. This 270 degrees of rotation again gives you a negative peak value, because again the coil is perpendicular to the magnetic lines of force. As long as it is perpendicular, we get the negative peak, that is the trough area of the graph, and further it continues to complete one complete rotation, that is 360 degrees of rotation. With this 360 degrees of rotation, we see that one entire alternating current graph is obtained, that is starting from 0 to its peak, to 0, again to the negative peak, and then to 0. So in one cycle of rotation, we see that the output is basically divided into a positive output and a negative output, which gives you the concept of alternating current. Let's consider certain theory application oriented questions as far as this chapter is concerned. The first one, you're given a cardboard and you're given two wires that are introduced in it, and you're shown the current direction in both the wires. You're asked to draw the magnetic lines of forces across both these wires when current is flowing in the given direction. In order to determine the magnetic lines of forces, we definitely go across by using our right hand grip rule. We know that current direction is in the downward direction. So I'm going to hold the wire in the direction wherein the thumb is indicating the direction of current. The moment I hold the wire in such a way that the outstretched thumb is showing the direction of current, I see that the curling of fingers is giving me the direction of magnetic lines of forces. So I determine the magnetic lines of forces by definitely using the right hand grip rule and indicating the direction of magnetic flux. So the figure that we obtain is something like this, wherein we are showing the magnetic lines of forces in terms of concentric circles across a current carrying conductor. The same thing, as I said, we go across a circular loop. So when we have a circuit that is connected across a circular loop, wherein the current is entering the coil in one of the arms and in the other case it is leaving the coil, we see that the right hand grip rule plays a vital role over here. We apply the right hand grip rule over here wherein the current is going in the upward direction. We see concentric circles that are moving in the anti-clockwise direction for the current going upwards, and for the current going downwards we definitely see that it is in the clockwise direction. The figure works out to be something like this.